in the dead stillness of orbit, far above the noise and clutter of Earth, a small satellite drifted silently against the black canvas of space. To most observers, it appeared unremarkable, just another speck among thousands of other metallic sentinels circling the planet. But inside this object, something revolutionary was unfolding, something that would shake the foundations of espionage, communications, and even warfare. The satellite was no ordinary instrument of data transmission. It was the world's first orbital quantum communication device, a machine designed to beam unhackable messages across the globe using the strange and ghostly laws of quantum mechanics. The story of this satellite begins not with rocket scientists or militaries, but with physicists tinkering in university labs decades earlier. For years, they studied a mysterious phenomenon known as quantum, a bizarre feature of reality in which two particles become linked in such a way that changing the state of one instantaneously changes the other, no matter how far apart they are. Einstein himself had called it spooky action at a distance, and for good reason. The implications were staggering. If this link could be harnessed, it could form the basis for a new kind of communication system immune to eavesdropping, resistant to interference, and more secure than anything conceived before. But the path to turning theory into reality was anything but straightforward. Quantum states are incredibly fragile. The mere act of observing them changes them, collapses them, destroys the information they hold. Sending such delicate particles through the thick soup of Earth's atmosphere, with its turbulent currents and electromagnetic noise, had proven nearly impossible, and yet some refused to give up. In labs from Vienna to Beijing, researchers pushed the boundaries of quantum optics, engineering photons, light particles entangled in precise ways, and trying to keep them stable long enough to send across kilometers, then across cities. Eventually, the challenge outgrew the planet itself. That's where space came in. With no air, no moisture, no bustling civilization spewing out electromagnetic chaos, the vacuum of low Earth orbit offered the perfect medium for clean, long-distance quantum transmission. So, after years of planning and a flurry of international collaboration, a sleek satellite was launched from a remote pad in China, bearing a payload unlike any before it. Its mission: to establish a secure quantum-encrypted communication channel between two distant points on Earth by beaming entangled photons through space. The satellite, nicknamed Mischius after an ancient Chinese philosopher who theorized about optics over 2,000 years ago, carried a crystal capable of generating pairs of entangled photons. Once in orbit, the satellite would split each pair, sending one photon to a ground station in one part of the world and the other photon to a station thousands of kilometers away. By measuring these photons, operators on the ground could create matching secret encryption keys. The magic lay in the quantum rule that any attempt to intercept or measure a photon would immediately alter its state, alerting the communicators to a security breach. It was like having a letter that would burst into flames if anyone other than the recipient tried to read it. The first successful transmission was both breathtaking and eerie. Scientists at a ground station in Austria received signals that precisely matched those being detected in China, thousands of kilometers apart. Two labs were now tied together by invisible strands of entangled light. The implications were profound. For the first time, humanity had managed to create a form of communication that, in theory, could not be intercepted or forged. It wasn't just a new kind of encryption. It was a glimpse into a new world where information could travel untouched by the prying eyes of hackers or even supercomputers. Governments took notice quickly. The strategic advantage of such technology was obvious. In an age where data breaches and cyber warfare threaten national security on a daily basis, Quantum communication offered a fortress of privacy. It wasn't just about secrecy, it was about trust. With quantum encrypted systems, financial institutions could transfer trillions without fear. Military commanders could issue orders without worrying about hostile surveillance. Activists could organize under authoritarian regimes without being exposed. The stakes weren't just high, they were existential. But not everyone welcomed this development. Deep in the shadows of cyberspace, a new kind of arms race was beginning. Intelligence agencies, long used to tapping undersea cables and slipping malware into enemy servers, found themselves staring at a technology they couldn't crack. In response, they began probing for weaknesses not in the quantum mechanics, which seemed ironclad, but in the human systems surrounding them. If you couldn't read the message, maybe you could compromise the satellite. If you couldn't decrypt the key, maybe you could manipulate the timing, jam the photon signals, or introduce false readings to create confusion. In-orbit missions continued its nightly passes over the Earth, showering the planet with bursts of entangled light. But every success raised new questions. Could the system scale? Could it handle the chaos of weather, clouds, and interference from other satellites? Could it work in daylight when photons from the sun drowned out the faint signals of quantum transmissions? And most importantly, what would happen when other nations launched their own quantum satellites, each one beaming unbreakable codes across the sky? Already, plans were in motion. The European Union unveiled its own initiative, aiming to create a continent-wide quantum network by 2030. The United States, after years of quiet development, began field testing prototype satellites in secret orbits. Even private companies, sensing an opportunity, started building ground infrastructure for what they called the QuantumInternet future, where all digital communications might flow through channels governed by the laws of physics rather than the frailty of algorithms. For ordinary people, the idea of a quantum satellite seemed distant, even mystical. How could something so abstract, entangled particles, secure keys, cryptographic protocols, have any bearing on their daily lives? But in truth, it was already shaping the future. Every time someone sent a message, entered a password, or shared their data traveled through a web of cables and servers vulnerable to attack. Quantum communication promised a future where that web would be shielded by nature itself. No amount of computing power, no clever algorithm could break a law as fundamental as quantum entanglement. Still, the system wasn't perfect. Ground stations required line-of-sight access to the satellite. Cloudy weather could disrupt the connection. Photons, even in space, sometimes scattered or vanished. And while the keys created by quantum methods were secure, they still had to be used by human-made systems prone to bugs, hacks, and corruption. The breakthrough was monumental, but not magical. It demanded careful oversight, constant monitoring, and a global agreement on standards and protocols. And yet, despite these limitations, the momentum was undeniable. Every test, every successful key exchange pushed humanity closer to a world where information could move without fear, where secrets could stay secret, where data, the lifeblood of the modern age, could finally be protected not by walls or passwords, but by the very structure of the universe. And all of it started with a single satellite gliding silently above a sleeping Earth, transmitting messages that no one could read except the intended recipient. The breakthrough in space-based quantum communication had not only proven that secure encryption was possible, it had proven that physics could be weaponized for privacy. No longer was security based on assumptions, complex algorithms, or mathematical difficulty. Now, it was grounded in the very laws that governed the universe.